Good morning, everybody, at least for the people that are here. So I guess you already heard quite a bit, especially from Jim Stone, about how to implement radiation and treat radiation in numerical simulations. And I found actually a nice quote on his slides saying that, you know, this is a really tough job or hard thing to do, compared especially to MHD or hydrodynamics. So this is a really tough part. So I'm not really an expert of any radiation modules in the Flash code. Nevertheless, I walk you through essentially two ideas which are there and might be a framework especially to be improved by you essentially and be adjusted to the purpose of your needs. So to start with, this is essentially one part of the equation. So this is the radiation transport equation you want to solve, and you can immediately see this is by no means an easy task, given the fact that this is dependent on the, any distance, the angle, the frequency, and if you like, even on time. This part is often omitted, and most of the magic actually in this equation resides in these opacities or emissivities in this so-called material functions. So these, you can place them like this, but most of the information, or a lot of the information, is kind of contained in these kind of black boxes. So in general, for the Flash code, and this is what we will focus on here, there is no kind of generic coupling so far to the hydrodynamics of this equation. Of course, this is what you are interested in, how does your radiation essentially affect your hydrodynamics or the gas dynamics or even the MHD. But so far, at least on this level, what I will show you, there is no direct or generic coupling to the hydrodynamics so far. But there is a module called 3T. 3T stands for 3 temperatures for electron, ions, and neutrals. Ions and radiation, and this module you might want to use, and this module kind of allows you also to couple the radiation field to the hydrodynamics. And in practice, it's actually what you do here, and that's why it's called diffusion module, is not you do a diffusion approximation, which we will see in a minute. So the radiation transfer unit in the Flash code is found in this directory here, and MGD stands for multi-group diffusion module. And the main idea here for the Flash people was so far to essentially couple the radiation, for instance, a laser beam, to the electron density, which is done by essentially by this integral here. And again, I want to stress that might be actually a good point essentially for further developments for your own purpose, and maybe even link it to astrophysical problems. Of course, if you do these high energy density studies here, you are dealing, with totally different timescales, talking about nanoseconds or something like this, microseconds at most, compared to our mega years or so in astrophysics. So that's a different realm so far. So this is the equation they solve, or there's a module providing the solution of a diffusion approximation of the radiation transfer equation, where you solve essentially for the, and you split this up in so-called groups of frequencies. So you bin your frequencies in a number of groups, and you can imagine something like 100 or even more frequency groups if you like. And you solve for the radiation energy density here, and you see how essentially why is a diffusion equation because of this term. And of course it has other sources because of the coupling also to the electron density. So if you essentially try to discretize this equation, there's you essentially end up with a so-called implicit equation, meaning that your advanced solution here depends also on the essentially advanced solution which you don't yet know. So you have to solve this implicitly, or you can come up with a set of coupled equations. And this is done by a library. So solving the implicit equation involves some essentially matrix inversion or coupling of a linear equation, a set of linear equations. And this is done by an external library which is not delivered with the Flash code, but you can download it. I can give you the link for this. So you have to install this library first if you want to use this multi-group diffusion module. And in the case if you don't use any flux limiter, and I think this was also introduced by Jim Stone, the diffusion coefficient looks like this. So it is essentially inversely proportional to the transport opacities and the absorption opacities. But if you have a look at this module, it also provides you with some flux limiter, which you might use and might come up with your own one, but there's at least an interface already to implement some flux limiter. If you want to use this this module, there is a way essentially to speed it up a little bit, in the sense that you do a decomposition not only in space, as the Flash code does anyway, using the AMR library, which is you do a space decomposition. You can use also, and this might be, as I said, useful to speed up the calculation, also a frequency decomposition. And how does this work? Essentially, you have to copy your entire mesh on various CPUs and have an identical copy, which is then treated by the individual diffusion solvers for individual frequency bins for individual groups. So what you do is you essentially use a runtime parameter where you can specify essentially the number of copies of your individual domains on your individual spatial domains essentially. And of course the default value here is 1, and if you increase this, you can split up or divide also your problem into frequency decompositions or frequency bins, where you collect the number of groups on a single CPU here. And the maximum number of groups per mesh, per copy of this mesh is you have to provide essentially during compilation time, because again, the flash code assumes quite often static arrays, so it has to know the number of groups you are dealing with, the maximum number of groups, similar to the maximum number of blocks per CPU. So that's in the same idea. So initially you have to provide, or during compilation time already, you have to provide the maximum number of groups you will use for your problem. So here's an example, assuming we have 6 processors which we can use, and have in total 100 groups, 100 frequency bins we want to use, and have a mesh, and copy our mesh here by we essentially use a mesh count of 2, so a copy of meshes of 2. Then it means for the domain decomposition, you use, essentially you divide your entire simulation box, so the spatial domains will be divided by 2 again, and you will have 3 spatial domains. And usually the number of copies here is copied meshes is of course 1. So if you don't use, for instance, this module, you will divide your entire simulation domain by 6 essentially, rather than by 2. So and then of course you divide your number of frequency spaces. That's actually a typo, that should again be the mesh here. Divide your frequency space also by this number, and in this particular case it means every other group will be computed on one processor essentially. So you do a division essentially by odd even groups. That means also that each processor only has to compute 50 frequency bins, 50 groups, instead of all the 100 here. So that's a fairly straightforward approach to essentially divide your entire problem not only spatially onto different CPUs, but also in a frequency space. But to test or to get the optimal speed, actually, you have to fiddle around with these numbers a little bit. So there is no very good guideline, essentially, what is the optimal parameter for a given number of CPUs you want to use. So you first have to try a little bit until you essentially run your production simulation. How to essentially initialize your setup here. What you have to provide is, of course, not only if you couple it to hydrodynamics, not only the hydro or MHD variables, you also have to provide all the information needed for the radiation here, meaning the specific energy or radiation energy per group you have to provide. And this can be a little bit simplified in the sense that you provide only either the total specific energy of the radiation given here. It should be the sum of the individual groups, the sum of the energy densities of the individual groups, or you can also specify a radiation temperature, which is then divided up into your energy density groups for the radiation. And there's a function called, which is more or less self-explanatory. So, you get your energy by providing, for instance, the radiation temperature here. But you have to be aware that this function also recalculates the temperature you put in here, and you will get back what is called an actual temperature, and this is the reason for this is that if you provide groups, frequency groups, you have an upper and a lower end to them. So if you do your Planck integration, you will not end up with the same, because you are not integrating essentially from 0 to infinity in frequency space, but only to, you have a discretized frequency space, and you have finite ends. And that means that your actual temperature might slightly deviate essentially from the temperature you provide there. So for given these bounds, the frequency bounds or the group bounds, these are runtime parameters for the multi-grid, for the multi-group diffusion module. And you have to be aware, strangely enough, you have to give these numbers not in Kelvin, which is usually the outcome for temperatures, or in frequency, you have to give them in electron volt. You just have to be aware of this, that the unit here to be used for the group bounds is actually electron volts. And then you use this recalculated actual temperature essentially to set as the radiation temperature in your simulation. So this is essentially a little bit of code within the unit. You want to initialize your problem. You provide essentially radiation temperature. In this case, it is, as stated here in the comment, it's just 1 electron volt, but the actual one is slightly smaller, most probably because of your finite bounds of your groups, of your frequencies here. And then you use the outcome and stick it in if you essentially initialize the actual radiation temperature in your simulation. And essentially, this function also provides you with splitting up the energy density, the radiation energy density of your groups, essentially given by this formula. So you do an piecewise integration of your Planck function from one group end to the other group end. Of course, you can do this also manually. You can set all the energy densities just by the number of groups you specified here. In this case, it's just 4. So, and this is even a more simple case in the sense that it provides you only sets a single group initially. So this is how the function looks like. If you want to stick in your radiation energy density, essentially, and in this case, the specific energy density by hand. There's no particular magic here. And of course, what you also need for this, and here comes, so to say, all the physics gets in here. You have to provide the opacities for your problem, and essentially to call the opacities as a simple call, and you get back you essentially provide, what you provide is essentially the density and the temperature, and you read off the opacities, or the opacities. You from this call you get back the transport opacity, emission, and the absorption opacities depending on your underlying table or scheme you use here. So, and of course there are a couple of predefined ways to get the opacities. The most simple is again something constant, so not varying with density or temperature whatsoever, so you get a fixed value. Or you use a multi-species opacities, which at the end of the day, just contains a table. And the table you provide, I think there's a couple of examples in the Flash directory as well. So this table has, two keys, namely the temperature and the density of the particular species you look at, so your ions or electrons in particular. And what the code does for you, or this call does for you, is essentially a bilinear interpolation. So the simplest thing you can do in this temperature density space to interpolate your opacities between the given tabulated values and the values you really want for your given temperature and density. Yeah, this is an example here of, this is actually straight copied from the Flash users guide. I haven't run this so far. So of the simplest case you can actually imagine, namely a gray radiation shock problem. Gray meaning you're going away again from your multi-group scheme, just use a single frequency. And in this case, you use this 3T module at the end of the day. So you have the temperature of the electrons, ions, and the radiation. But in this case, you fix, or you essentially, you have an equal temperature for the ions and electrons. You can do this by a heat conduction module, for instance. And initially there's a step function, and what it should evolve to is what is called a steady state shock. And this is essentially pictured here in these two graphs. On the one hand, the temperature, the other hand, the density. And as you can see, there's an analytic solution to this problem provided by Lori. So essentially, you can reduce this problem to a fairly simple, or to an ODE, which you then can solve using a Runge-Kutta approach or something like this. And you can compare then your result provided by the Flash code with this analytic solution. And this looks actually fairly well. So in principle, this module should work, especially for a gray approach. So meaning if you use only a single frequency. But there's also an example for 4 groups, 4 different frequencies, and so this is an essentially time evolving problem. So you have a step function in the temperature, and of course eventually heat should flow from warm to cold regions. And here you don't have in this sense an analytic solution, but you can kind of watch what happens there over time, and you see how essentially you started off with something with a step function in both temperatures, and then they evolve independently and get smeared out while the colder region gets warmer, and vice versa. So this is very briefly essentially outlining here a radiation diffusion module, which is already present in the Flash code, but is still, at this point it is a little bit questionable how applicable it is essentially for astrophysical problems, because it's not yet tested for this, and it didn't also provide all the right opacities. But you are essentially encouraged to try this out and apply this module for your typical molecular cloud, for instance, so for typical astrophysical environments. And also, I think that the most crucial thing is, of course, this module is damn slow. So you definitely want to see how whether you can use it in a highly dynamic simulation, or whether essentially your simulation will grind to a halt just because of the diffusion model here. So this is essentially a warning, but I think it is actually for the Flash code a quite good starting point. And if one gets a handle to improve this and essentially adapt it, in particular for astrophysical problem, that might be a good way to include essentially radiation into our simulations. Yeah, here's again a summary of the units which are involved solving a coupled problem of radiation diffusion with the hydrodynamics, and you see that apart from the hydro, you can have an heat exchange between the ions and electrons. Then the diffuse model is actually solving the radiation diffusion problems. This module here implements the split up of different frequencies. You need the opacities and can also include conductivities. And then there's something which is a little bit more towards these laser experiments. Essentially is the energy deposition of the laser energy. Okay, now I want to, so this is essentially a diffusion approach we were talking about, and this is often good for essentially also for optically thick regions where we have a lot of scattering and where the radiation is essentially really diffusing rather be transported along a single direction because of all the scattering events. And there's another approach implemented in the Flash code, and unfortunately so far not yet in the latest release, so not for Flash 4. It's only available up to the version 2.5. So this is the opposite approach, if you like. You solve your radiation equation along rays in neglecting exactly these effects of scattering and diffusion. And then obviously your radiation transport equation gets very simple. So essentially it's just an exponential damping of your initial intensity, and the damping is done by the optical depths. So at the end of the day, you have to calculate the optical depths along a path, along a ray, and this is essentially by integrating the density which provides the opacity for a given frequency, if you like, but this is all here in this case frequency independent. You just have to integrate. I'm saying just, this is also not really a trivial problem. Integrate along a array, along a long and radial distance from your, if you talk about a point source. So, and I think this is also something Jim Stone already told you, that in principle there are two different ways to do this ray tracing, namely by so-called long characteristics or short characteristics, pictured here roughly. So for the long characteristic, you shoot essentially a ray from the source to all grid points you want to in your simulation, whereas for the short characteristics, you always start essentially at the boundary of your grid and walk along the ray just internally in your single grid to the opposite side. And of course, these two approaches have pros and cons. The long characteristic has the disadvantage, you have a lot of essentially redundant calculation if you get closer and closer to your source, and so hence it is relatively slow, And I think it should scale with something like n to the 4th, where n being the number of grid points here. For the short characteristic, it is faster. Obviously, you're not, traversing individual grid cells with many rays. You're only using a single ray, but it has essentially difficulties a little bit to handle point sources. I mean, hitting a single source here is not so trivial. So and then Eric Rekost essentially came up with a method he named hybrid characteristics, and for the actual ray tracing, walking the ray, it's actually based on a long characteristic approach. So what you do here is to essentially, and the main idea was here to speed up the calculation, go from this fairly slow, general long characteristic approach where you traverse your entire simulation box with many rays. So what he did here, he used essentially the structure of the underlying AMR grid, of the block structured AMR of Flash, and did a traverse essentially from the source, which is here, to using a long characteristic approach to walk within a block, for instance, or he calls it patches, to be a little bit more flexible, to be used also with different AMR techniques. And then what you have to do if you walk in particular here for the to the grid cell centers, to the cell centers where you have essentially your variables are defined, you have then to interpolate them to the boundaries pictured here, and then what you do is essentially you communicate these phase values, the boundaries, to be added up eventually to get the entire column density. So you essentially have to build a list of phase values which a single ray is traversing, and this is a little bit similar to the tree algorithm we talked already about. So you build an internal list of, he calls it patches, which must be added up essentially if you want to get the column density at particular cells here away from your source. And originally, so that's actually the main idea here I outlined here is why Rekost essentially calls this approach hybrid characteristics. So I told you that actually the internal walk of the rays here is still based on a long characteristic trace here, but at the end of the day you do this only locally on each CPU up to your patch boundaries, so in our case block boundaries, where you store the phase values and then communicate these phase values. Hence you get an speed up. You don't have to traverse a single ray to your entire simulation box. That's why he calls it hybrid characteristics. Kind of takes a little bit of both, of the getting the source fairly easily using the long characteristic, but then communicating only the phase values. It's a little bit similar to this idea of a short characteristic. Initially, to get this list of of patches which are traversed by ray, so you can which phase values essentially you have to add up. He used what he calls a patch mapping approach. And initially, what he did actually copy on each CPU the entire grid. And you see, even independent essentially of how well refined a certain block is, he always generated a grid, an entire grid, based on the smallest grid cell in the entire simulation. And you see you get a lot of redundant information. The big blocks copied many times to each grid cell. And this initially, this version limited the simulation quite dramatically, in the sense that you could only go to a low, I would say a low resolution simulation, using at most refinement levels of the order of 7 or so. And this essentially, Thomas Peters improved this substantially because all these redundant information here you can locally easily recalculate by knowing all the properties of your block. So what you do is you essentially communicate not the entire grid, but only the AMR tree structure. That's totally sufficient, and to essentially to recalculate here the list of phase values you want to add up to your column density here. So this got away from this limit of low resolution runs, and in practice you could do as any high resolution run you want to do, because the tree itself is fairly slim, which you communicate. Yeah, and as I said, so far there is no, at this point there wasn't any, or is no coupling, is no scattering, and so on. So the main purpose for this entire approach, so far we only calculated, the column density, and the main purpose here is to calculate essentially the ionization at a given point away from your source in your simulation box. So this was also provided by Eric Reichhorst here in his 2006 approach or paper, coupling the entire scheme to ionization. And of course, then you have to solve a couple of equations, namely the rate equation you have to solve. So how much, depending how much ions or how much ionized hydrogen you get, depends then of course on the photoionization rate here, which of course depends essentially on the star, and we know that's mainly the massive stars which ionize the gas, and I guess you will hear quite a bit later on by Chris McKee about massive star formation. I also will show you some results in a minute. And not only by photoionizing you, by photons you will ionize your gas, also by collisions, which is also included here. And then you have to account for the recombination rate, which is done by a fairly simple approach, just a recombination rate factor essentially getting in here, just depending on the temperature here in a simple way. So these are the equations you want to solve, and then if you ionize a gas, you also heat up the gas. You have to account for this, so you get a photoionization heating rate, essentially, which you include then in your hydrodynamics to heat up the gas. And not only it's heated, of course, it can also cool by metal line cooling. So this is also included in these calculations, or in his original module here. And because this is a fairly stiff equation, solving the rate equation here, so what you have to do, you essentially have to subcycle. You use your thermal time step for this particular problem and try to find a converged solution for the ionization fraction and the temperature, which depend on each other. Okay, this is a summary of this ray trace approach from Reichhorst, including the ionization coupled to ionization physics. And here a few examples I want to flip through, namely, first of all, essentially a clump which is irradiated, in this case, by two sources, here and here. And this is calculating the column density individually for these sources, and what you see, of course, here is a high density neutral atomic clump, and of course the column density increases then dramatically if you hit once the clump while you walk along your ray here. And this, of course, has then effects on the ionization, or the amount of neutral hydrogen you get. And this is essentially a combination of these two sources. You get, nice kind of shadows here. And this is essentially just the initial step without including, the time evolution or the heating of this clump. So this essentially to demonstrate how this method works, and it looking at these pictures, it looks exactly what it should do, namely produce shadows essentially behind the high density clump. And this is essentially, if you evolve such a system, this is a little bit a different setup, but very similar, including the photoionization heating. Of course, what happens is over time you disperse your clump, and here initially there were two clumps at this point, and this is a time sequence, either here the density and here the ionization fraction, or the H1 fraction. And because you heat up the clump, it dissolves over time, and then of course you lose all your essentially your atomic hydrogen, and everything gets ionized eventually. Okay, and then that was actually the reason why Thomas Peters worked on this so hard to improve this method and make it also available for high resolution simulation. I want to show you a few examples and about all the details on the formation of massive stars. I guess Chris will tell you later on. So this is essentially just outlining some of the main results here. So this is already what he did here in this example is a collapse of a massive gas clump, gas core of 1,000 solar masses. This is already evolved a little bit, hence you already formed a zinc particle. And then I told you yesterday we can use the information of the zinc particle to feed back, essentially in this case, ionization heating, having the reading of, for instance, the mass, using the mass of the zinc particle, and read off the luminosity and the temperature from a predefined sums table. And then we know the temperature and the luminosity, which we need to essentially evolve the source. So we have the source is variable over time because the star is accreting mass. It gets getting more and more massive, and more UV photons will be emitted from this source. So here's a little animation after the collapse and forming the first few massive stars here. And so the entire thing was rotating. We form first a kind of a filament, a disk here, which you see not only one but a couple, so 2 or 3 massive stars are formed and start to ionize the gas, start to heat it up. So you get these so-called H2 regions, which are at this early stage in the ultra-compact stage here, and if they're below 0.1 parsec or so, they are everything else but spherical. If you watch this again, they're highly variable in time and space. So you can't really, for instance, age date these compact H2 regions just by their size, because they're not expanding with the sound velocity, but they might be quenched every now and then shrink and grow again, just because also of the unsteady accretion you find onto the star. Yeah, this movie I think I showed you yesterday is essentially the same, just volume rendered nicely to for presentation purposes. You see the how the gas is heated up here by while watching the pressure. Essentially, you see almost little explosions, and eventually, if you wait long enough, the entire thing becomes a little bit more spherical, but is still highly structured. Yeah, just to show you a few quantitative results here based on this simulation, for instance, it is interesting to see, whether the feedback from ionizing radiation might actually shut off the accretion, and it looks like it cannot. So, and this is an intrinsically 3D problem, so there's always, despite the effect of the high pressure, there's always a path essentially for the gas particles to fall onto the star, because your degrees of freedom in 3 dimensions is quite large. So there's always, in particular here in this case through this filament, the star is more or less continuously fed by gas. It is so the ionization feedback does not really shut off the accretion, but what it does eventually in this particular case is, if you have seen there's many, it's not a single star which you form here, but it's many stars. You always form your massive stars in clusters. The gas fragments, because it's so massive, it's so dense, and the individual stars, might they be low or intermediate mass stars even, they essentially get the gas from the envelope from this collapsing cloud core, and kind of prevents the accretion onto the more central object. Eventually the accretion to the central object can be kind of shut off here by the fragmentation, so by the formation of secondary stars. Here I'll show you some images. This relates essentially to Stella's lectures before that, how important it is essentially not only look at the density or temperature in your simulation, but you also want to move to the observer space and see how these objects would look like in particular frequency bands, with particular instruments. And Thomas Peters did here, for instance, synthetic maps of radio emissions, so 2 centimeter lines, which you can observe with the VLA here. And one thing was to test, for instance, the morphology of these H2 regions. And what you see is essentially in a single run, we come up, or in a single run, the morphology changes dramatically by time, but also by viewing angle. So telling us that we don't actually really need different theories to come up to explain all these different morphologies which are observed as well. And there's no magic behind this. It's most probably a point of at which state into the evolution you look at a particular compact H2 region, or at which viewing angle. So essentially all the morphologies can be reproduced. So you don't have to come up with something specific for a given shape of your H2 region. And a similar approach you can do and ask yourself, whether we have seen that these massive stars produce quite often bipolar outflows, and you can ask yourself, does this in any respect resemble the outflows which are observed? And of course, first of all, what you have to do is, again, do synthetic maps, try to do exactly to put essentially your simulation into the observer space, and then recalculate the typical numbers from these synthesized observations, and then match them to real observations. And this is also work done by Thomas Peters and Pamela Klaassen. And analyzing these simulations, it turns out, so the summary, it turns out that these ionization-driven outflows are most probably not the main driver of observed outflows. So there's something missing, and maybe the missing thing is that you have to include somehow the outflows coming from all the low and intermediate mass stars you see there. But in this simulation, there are no outflows present from these stars because they are not modeled. So that could be an explanation. So it kind of matches the observation, but all these they have the tendency to be really on the low end, where it seems there's a missing piece here for driving these outflows. Yeah, and there's a continuous development by Lars Buntemeyer, PhD student in my group, essentially trying to extend this ray tracing approach where we have seen, so you do a ray trace essentially from a point source to any point in the grid, to extend this to use essentially parallel rays and use them with many different angles, so you can handle scattering events as well. And we are testing this right now, whether this is a viable approach or whether it is too time-consuming. And here are a few results. For instance, this is a density structure of a disk here, and if you do your parallel ray tracing with about 100 angles or so, you can kind of recover the temperature structure, and then you can compare this, for instance, with other tools, for instance, with RADMC, and see whether you get a similar temperature structure for the given density. Or there's a diffusion problem as well, so radiation diffusion in a highly optically thick regime. In principle, it seems to work, but we still have to work essentially on the efficiency of this method, and also find out what is the minimum of angles you want to use to get a reasonable result. And so far, it turns out we need about at least 50 angles, which is quite a number. So this is comparable to essentially have 50 point sources in your simulation with the point source ray trace. Good. I think that's only the task for you now, which I can present here. So what you could do is essentially, if you have enough time, you can migrate all this ray trace approach, for instance, from Flash 2.5 to Flash 4. I think in this respect we need a lot of help. That's not too straightforward. But I also, of course, recommend you, if you have some time the next days, try the diffusion module also in the Flash code, and get a little bit of feeling in particular about the performance of this multi-group diffusion approach. So thank you. Any questions here? Yeah.
So Robi, with respect to the outflows.
Right.
All right, so you don't have the resolution to self-consistently launch them in this simulation.
That is right, yeah.
And you didn't put them in by hand. Okay. You didn't use a subgrid model for them. Right.
So yeah, here the question was essentially the outflow, the ionization-driven outflows, essentially the pressure-driven outflow, not the magnetized ones, whether they can reproduce the observed properties. That was the idea of.
Right, but we know from. Right, but we know from interferometer observations, this is going back to Hunter Future's work, right? That you do get jets from maybe not O stars.
Right.
Clear, but certainly up to late O stars. Right. You get these very well-defined collimated jets.
They are missing in these simulations. Yeah.
Right. So, but in that sense, you sort of knew already, right, from the observations that the outflow had to be jet-driven and not ionization.
Yeah, in this respect, you can say that, double check whether they are sufficient. Or, I mean, there are also regions, I think, where you're not really resolving the jet light outflows, but still see a little bit like messy pictures like here.
Oh, sure. I mean, yeah, Henrik showed that you often see a total mess
Yeah.
if you don't look at the interferometer, but then
Right.
if you zoom in and look at the interferometer,
You get more and more.
Actually, you can break your
Yeah.
total mess up into a bunch of individual jets.
Right, right. So I mean, this is something we are working essentially on, to put in a subgrid model for all the other stars for the outflows, and maybe also to get a handle on the, how maybe we can actually adjust also our subgrid model with comparing them to the observation, not putting too much energy or too little.
So if I can just make a point, so sometimes there's evidence for wider angle lens, and there's the case of low mass stars. So depending upon what tracer you're looking at in the molecular gas, you might see a wider component. If you're looking at a shorter wavelength, you see more of the shocks of a collimated jet. So it might still be worth doing the comparison to look at the lower velocity material and see if that makes sense.
All right.
Okay.